So, welcome back student to the next class of Introduction to Nonlinear Optics and its application. So, today we will going to have three very important going to learn very important concept. What first one is the Manley-Rowe relation, which is very important, then the energy conservation under second harmonic generation, and finally different kind of phase matching. In the last class we have learned about the phase matching and find out that there is a bandwidth delta k equal to 0 is the condition of our phase matching. So, delta k equal to 0 is the condition of our phase matching, but we find that even delta k is not equal to 0, we get some kind of phase matching, and we also able to figure out what is the bandwidth, that if any external parameter x through which delta k is depending on, then what is the tolerance of this external parameter in terms of delta x, that for which we are getting the phase matching. And this phase matching delta k tolerance level we fixed at this 4 wave half maxima point. So, that we have already discussed in the previous class. So, today we will going to discuss more important things like Manley-Rowe relation. So, let us go directly. So, what is the meaning of Manley-Rowe relation? Before studying the Manley-Rowe relation, we will again go back to our original to mother equation, which is evolution equation of E2 and E1 as shown here, that inside the material if we have two waves E1 and E2, then E2 and E1 will going to evolve under this master equation, which is the coupled equation. Now, if I want to find out what is the corresponding intensity, then again we will going to use a very old expression that we have been using for last few classes. So, intensity is half epsilon 0 C n mod of E square. This is the relationship between the intensity and the mod of E square term. Now, what happened? That we try to understand, because of this energy exchange, is there any quantity which are remain conserved. So, obvious question is the energy is conserved here, because E2 is gaining some kind of energy. Initially we find that E2 was not 0, but gradually it is getting some energy from E1. So, now in the previous class the way we have calculated E2 was not physically correct, because we consider E1 as a constant. So, that means E1 is constantly feeding the energy to E2, but E1 is not changing by itself. So, that means the energy that is coming is not the total energy. So, the total, if I calculate the total energy in under such condition, we find the total energy is gradually increasing, because E2 is gaining energy, but E1 is not losing any kind of energy. So, that is why that treatment was not totally correct, because that approximation is correct up to certain limit, but after that we need to put more rigorous calculation to find out exactly how E1 and E2 going to evolve. That we will do in the future classes. But today we are going to learn that if I2 and I1 is the intensity related to E2 and E1, then what is the relationship between I2 and I1? This relationship is basically called the Manley-Rowe relation. Well, this is my mother equation. These two equations are always there. I2 and I1 already I defined in the previous slide. Now, next what we are doing, we just make a derivative with respect to z over I2. So, if I make a derivative with respect to I2, then eventually we are making derivative of this quantity, because half epsilon 0 C n 1 all are constant. So, if I make a derivative in the left hand side, so derivative will only be over this mod of E1 square, because E1 is a function of z. Here please consider that I am considering please note that we are considering E1 as a function of z. Previously when we calculate when we solve this differential equation, we considered that E1 is a constant, which is not critically true, but here we are putting more physical we put more physical emphasis, and try to find out what happened if really E1 is changing with respect to z. So, now obviously, if E1 is not function of z, then we find di d2 di dz is basically 0, because there is no change of I also I1, but here we are considering that change also. So, now what is the value of this derivative? So, E1 is nothing but E1 E1 star. When it is E1 E1 star, when I make a derivative, there are two functions. So, first function derivative of the second function derivative of the first function. Straightforward derivative rules we are using, and then what we will do, we just put the value of E1 from value of this derivative from this expression. So, when we use the value of this derivative from this expression, in both the cases we find that omega d c n 1 and I will come, and if I take it common, then it should be E1 and multiplied by this quantity. But please note that this is d E1 star dz. So, if I make the complex conjugate of this quantity, I will have a minus I. So, let me do that, d I1 star dz. So, it is omega d c n 1. This E1 star become E1 and E2 become E2 star, and then e to the power I of minus delta k z, because we are taking the complex conjugate of this differential equation. When I take the complex conjugate of this differential equation, we have E1 E2 star. So, here you can note that we have E1 E2 star, and one E1 was already there. So, this that is why we have E1 square. In the similar way, the next term we just multiply with E1, because this term we do not need to make a complex conjugate, because already this term is here. So, we will eventually have E1 star square E2 and e to the power I delta k z. So, these two terms, if you note very carefully, is a complex conjugate of each other. So, this term and this term are complex conjugate to each other with a negative sign, So, now if I say this is x plus I y, the second term is x minus I y, and if I subtract, so we have 2 I y term. So, this I will come here and another I is sitting outside. So, if I multiply these two and one negative sign here minus 2 I. So, I will get a plus real quantity here. This has to be the case, because in the left hand side we have a real term. So, entire term has to be real. Anyway, what should be the value of d I 2 z dz? We calculate d I 1 2 d I 1 dz. Now, we calculate d I 2 dz. So, this is basically the procedure is exactly same. So, if I do the calculation, then I will get exactly the similar kind of expression. Note that here we will going to use this equation, which is I d omega c n 2, then E 1 square e to the power I delta k z. That was the value of E 2. Now, what we will do? We will just there was a negative sign for E 2. So, now we make a complex conjugate of the entire quantity and then multiplied by E 2. When we do that, complex conjugate gives this minus. So, that is why there is a minus, and d omega c n 2 we can take common for both the cases with I, and then this term become positive and E 1 become E 1 star square, and then E 2 is multiplied. The next term is simply E 1 square E 2 e to the power I delta k z. So, now if I put these two terms side by side, this is equation 1 and this is equation 2, we find that these two terms are related to each other with a negative sign. So, d I 2 d is I epsilon 0 c n 2, and this n 2 will cancel out here, this n 1 is cancel out. So, if I compare, then find inside this bracket we have E1 star E2 with a negative sign, but here we have E1 star E2 as a positive sign. Here also we have E1 square E2 star term, but here we have again E1 square E2 star term, but with a negative sign. So, overall we will have one very important expression, and this expression is shown here, which is the relationship between I1 and I2 in their differential form, that d I1 dz is equal to d I2 dz, and this is basically called the Manley-Rowe relation. This relation basically suggests that if I take these two terms in a one side, this relation basically suggests that I1 plus I2 is equal to 0. Now, I1 plus I2 is the total intensity. So, that means the total intensity, the change rate of change of total intensity is 0. That means the total intensity should be conserved under second harmonic process. So, this is the next thing, that we will going to prove. After doing the Manley-Rowe equation, we can say that the total energy is conserved. So, Manley-Rowe equation is something which basically tells us the total energy is conserved. So, I1 plus I2 is here, I1 plus I2 is here. So, if I now make the total energy is proportional to I. So, rate of change of total energy is nothing but I1 plus I2 and then the derivative. Now, if I apply the Manley-Rowe relation, that d I1 dz is equal to minus of d I2 dz. So, this basically gives me that this quantity will be 0, and when this quantity is 0, we have this expression which suggests that energy is conserved. So, U, which is the total energy, is constant. So, very important physical outcome, that during the second harmonic generation process, whatever the expression we find out, which is amplitude, the evolution of the amplitude of the second harmonic and the fundamental, but the equation is such that the total energy remain conserved, and that should be the case because there is no external energy or absorption is there. So, that means there is no addition or subtraction of the energy, only there is the exchange of energy between the wave E1 and E2, and if that is the case, then always we should have the total energy conserved. Now, the next thing is what about the photon numbers? The photon numbers is, if I say n omega is a number of photon of frequency omega and in 2 omega is a number of photon of 2 omega, then the total energy is n, total number of photon multiplied by h cross omega, and n 2 omega multiplied by 2 h cross omega, because here the frequency is 2 omega. So, that is the total energy, because for one photon we have the energy h cross omega. If n number of photons are there, we should have n multiplied by h cross omega to get the total energy for the photon having frequency omega. So, this U is total energy. So, now we try to use the relationship that we just derived by using Manley-Rowe relation, that the total energy is conserved. If I do, then it should be du dz, which is equal to 0. Basically, this leads to a very interesting expression, that omega d n omega dz is equal to 2 omega d n 2 omega dz. Mind it, we have a quantity like d n omega dz. Now, d n dz is basically the rate of change of photon numbers. Now, inside the system what happened, the second harmonic waves are generated from the first fundamental wave. So, if this is E1, E2 is generating, E2 is generating means the number of photon is there which is not conserved. So, E2 is generating means initially the number of photon may be less, but gradually it is getting some kind of energy through the photon number. So, the number of photon may not be same. So, that is why there is evolution of number of photon also. So, finally, we have one expression which suggests minus half d n dz is equal to d n 2 omega dz. That means, we are getting number of photons, the number of photon change the number of photon change for omega frequency, and half of that will be equal to the number of photon gain of 2 omega frequency. So, this is the number of photon change for omega frequency, and if I make a half of that, that means the rate of change of photon, that is changing photon number, that is changing for omega photon. The negative sign means it is reducing. The rate of gain of 2 omega photon is half of that, and that is true because we know that 2 omega is generated because of the fact that there are 2 omega frequencies are there. If I now try to find out this picture, we can say that 2 omegas are merged to generate 2 omega photons. So, there are 2 photons with omega frequency, they collapse and they form 2 omega. When they collapse, that means there is a change of photon number, and since there are 2 photon that is changing, if I make a half of that, then we can say that the number of photon that is generated because of the collapse of 2 photon is dn 2 omega dz. So, this is the photon number in terms of photon number we can have the Manley-Rowe relation. So, this is a Manley-Rowe relation, but in terms of photon numbers. Okay. After having this expression, now we will go to a very important concept or very important thing especially in second harmonic generation, and that is phase matching. So far we mentioned that delta k equal to 0 is our phase matching condition. Delta k equal to 0 is our phase matching condition. So, let me write once again, delta k equal to 0 is our phase matching condition, but we never mentioned how to make delta k equal to 0. We assume that if delta k equal to 0, we have a phase matching, but now we need to understand that what happened when delta k equal to 0 we know, but now we need to understand that what is the procedure to make this delta k equal to 0. So, one way is that this is called the birefringence phase matching. There are 2 phase matching system we will going to cover in this course. One is birefringence phase matching and another is quasi phase matching. So, let me very briefly describe what is the meaning of birefringence phase matching and what is the quasi phase matching. So, in birefringence phase matching, as the figures suggest, that for this phase matching, if you remember, our condition was n omega has to be equal to n of 2 omega, but due to the presence of dispersion, this condition never valid. But if n omega is not equal to n of 2 omega, then one thing we can do, that we can equate n e of 2 omega and we can equate to n o of omega. So, that means n e means there is a possibility that we can have the refractive index, there is a possibility that we have a refractive index which is equal to the refractive index at omega, but this refractive index for extraordinary ray and this refractive index for ordinary ray. So, this curve suggests that this value is for, this is a circle. So, that is the refractive index of ordinary ray at frequency omega. This is a refractive index of ordinary wave at frequency 2 omega, and if this quantity is there, this is a refractive index of 2 omega, but this n e will change as a function of delta, this function of theta. So, if this theta is there, so for different theta we have the refractive index different. This is optic axis. So, that optic axis, these 2 quantities are same, but what happened that at that particular point there is a possibility that we will have 2 things are same. So, this is called the birefringence phase matching. So, we will discuss in detail what is the meaning of birefringence phase matching and how we will going to achieve that. So, this is the one part. Second part is quasi phase matching. Quasi phase matching is also very interesting. In quasi phase matching, what we will do, we just change the phase by rotating the crystal structure. So, if the direction of the crystal is this, if I rotate the crystal in opposite direction, so that we know that if I change the crystal with their axis, so what happened that their coefficient is also going to change. So, if I rotate the crystal, there is a possibility the coefficient of d will going to change, and that means d now become a function of z. So far we are dealing with the other quantity, but considering d as a constant, but here we can see that d can also change periodically. If we change d periodically, then there is a possibility that we can, if there is a phase mismatch between E and P polarization electric field, we can by rotating the crystal we can fix it, and when you fix it they should be equal. So, this is the concept of quasi phase matching. So, again we will learn this quasi phase matching in detail. So, now what is the birefringent phase match? As I mentioned, this birefringent phase match n omega has to be n 2 omega, and this is the phase matching condition. From this phase matching condition, one can easily find that my condition of phase matching has to be this, which we have already discussed in the previous class. So, now the condition we need to find that n omega is equal to n of 2 omega. Now, n omega is equal to n of 2 omega, is it never possible, and why it is never possible? Let us try to understand through our dispersion theory. So, we know that this susceptibility can be represented as a function of frequency in this way, and then we can write this susceptibility if this is a plasma frequency, and if I put this is delta, this is the thing we have already done. So, I am not going to very detail about that. So, I believe all of you understand this susceptibility, first order susceptibility will be a function, and I can write it as a real plus imaginary, and the real part is this, and imaginary which basically gives you the absorption is this one. So, now refractive index is epsilon 0 omega and 1 plus this. So, if I expand these things, then it should be real plus imaginary, and we know that 1 plus this quantity basically gives us the refractive index. The real part is basically refractive index, gives us the refractive index. This quantity, this susceptibility is function of omega. So, refractive index has to be function of omega. So, once we have 1 plus this, and now the important thing is that the explicit form is given here. How this quantity will vary as a function of omega is given here. So, we have this functional form, and if I try to find out what is my refractive index, then we just plot it, and when we plot it we find quite interesting thing, and that is this. So, as I mentioned, my refractive index n square become function like this, and this is the condition. Let me go back so that you can understand what I am trying to say. So, this is the function. So, this delta, so x r it is delta square plus gamma square omega square. Delta is a omega 0 square minus omega square. If we consider my damping is very small, then this equation I can approximate as this. I can neglect this term. If I neglect this term, we will have omega p square divided by delta. Delta were these things. So, omega p square divided by omega 0 square minus omega square will be the functional form of psi r, which is the real part of this. So, that means psi r will be omega p square divided by omega 0 square minus omega square. So, when I put this psi r into my equation of refractive index, then what we find, let us see. Well, as I mentioned, I just replace this omega r to this quantity. When I put this quantity omega p square divided by omega 0 square minus omega square, then we have a functional form. Now, if I put this functional form here, so what happened, that we will have a curve like this. This is called the dispersion curve. This is called the dispersion curve. N is a function of omega, is called the dispersion. So, this dispersion suggests that if I increase omega, then if omega is here, then omega, then n 2 omega will be somewhere here. So, n of 2 omega will be always greater than n of omega, at least is in this normal domain. This is called the normal dispersion. In normal dispersion, what happened, n of 2 omega, that means n at higher frequency will always be greater than n of the lower frequency. So, now the dispersion curve readily suggests that this condition is not valid. If this condition is not valid, the next important issue, that what to do in order to get the phase matching, because my phase matching suggests that my n has to be equal to n of 2 omega. My phase matching condition basically delta k equal to 0 suggests that I should have n of 2 omega will be equal to n of omega. Now, if a material has a dispersion, and if this dispersion curve look like this, which supposed to be the case, then we will never get the phase matching condition. So, if we get the if we never get the phase matching condition, then the only situation we can have to use some kind of crystal where we have two different kind of refractive index. One is ordinary refractive index and another is extraordinary refractive index. And maybe there is a possibility that ordinary refractive index and extraordinary refractive index may match at certain angle where we can have our phase matching condition. So, we will in the next class we will going to learn what should be the crystal and how we will get this phase matching for this kind of crystal and detailed calculation. So, with this note, let me conclude my class here. So, see you in the next class. Thank you.